Okay, so here's a function f of x is x plus 1 over x minus 2. Notice the domain says x can't be 2. It is 1 to 1. You don't have to verify that. You could produce the graph of it with a graphing calculator or a computer and see that it passes the horizontal line test, but the book is simply telling us it is 1 to 1. Find its inverse function. So remember, the first thing you need to do is to swap the role of x and y, and then try to solve for y. So if we swap x and y, we get this. Now what you have to do is solve for y, and remember when we say solve for y, you need y and nothing else on the left, and the right-hand side has no y in it at all. So can you take this and manipulate it to just have a y on one side and nothing involving a y on the other? So try to complete that. So the first step is to multiply that denominator to both sides, then distribute. So I have xy minus 2x equals y plus 1. Now try to get all the y's on one side and all the non-y's on the other. So if I move this y over there, it becomes negative, and if I move 2x over here, it becomes positive. But the point is, I have all the y's on one side, and I have none of the y's on the other side. What you really hope happens at this point is you can now somehow factor out a y and solve for it. And this one you can. You factor out the y times x minus 1 equals 2x plus 1, and then I can divide the x minus 1 over. And we've managed to get just y on one side and no y's at all on the other. We have solved for y. So is this the inverse function? So let's check. So our original function was x plus 1 over x minus 2. So I plug that in. Let's just, I'll just remind us. F of x was x plus 1 over x plus 2. And the question is f inverse of x 2x plus 1 over x minus 1? That's what we had sort of solved for and found. And now let's check it by taking one and composing it with the other. F inverse of f. So I take f of x and I plug it into f inverse. Now I need to, oops, get rid of my writing because I put it in exactly where the next stop was going to go. Okay. If you multiply numerator and denominator by x minus 2, it simplifies a bit. 3x over 3, hey, that's just x. That's what we were hoping to get out. You could also check by taking f inverse and plugging it into f, multiply numerator and denominator by x minus 1. If we do that, I'll have to erase this in a second, but I know this step can throw people off. Okay, so what we have now is we'd have 2x plus 1 over x1 times x minus 1 plus x minus 1. That's just the numerator over 2x plus 1 over x minus 1 times x minus 1 minus 2 times x minus 1. And that's the denominator. And now this x minus 1 cancels that. This x minus 1 cancels that. And that's exactly where the next line is going to come from. There. Simplify all this down, and again, you just get out an x. Okay, so another example. F of x is x squared plus 1 if x is bigger than or equal to 0. This parabola, if you graphed the whole thing, it would look like this. Is this 1 to 1? No, it very much fails the horizontal line test. However, what they've done is they've done what's called restricting the domain. I have the same parabola, but I only have when x is bigger than or equal to 0, and I'm not drawing the other part of it. Now it is 1 to 1. It does pass the horizontal line test. So what can happen a lot is if a function fails the horizontal line test, that means the function isn't 1 to 1, the function doesn't have an inverse. What you do is you say, well, let's restrict the domain by not drawing part of it so that it does pass the horizontal line test. And now this restricted function does have an inverse. So how do we find the inverse? Okay, so this is just what I just talked through, sorry. So if we restrict the domain by only letting x be bigger than or equal to 0, it does have an inverse. So let's find it. So swap x and y. X is y squared plus 1. And since we had the restriction x has to be bigger than or equal to 0, when we swap x and y's, that means y has to be bigger than or equal to 0. So now try to solve for y by subtracting 1 to the other side and then taking the square root. Okay, normally what you would do is you'd say y squared equals x minus 1, and then you get y is plus or minus the square root of x minus 1. This is not a function. Why is it not a function? Because one input is going to give me two outputs. But the restriction was y is bigger than or equal to 0, which means I don't want plus or minus the square root, I just want the positive square root. Okay, so there's your inverse function, which you can verify by plugging them into one another. So I take f of x and I plug it into f inverse. I have the square root of the input minus 1. The ones cancel. And this is a really common mistake students make, okay? So if the ones cancel, we get the square root of x squared. The square root of x squared is not x. The square root of x squared is the absolute value of x. Okay. For example, if x equals 2, x squared is 4, and root 4 is 2. Hooray. But if x equals minus 2, then x squared is 4, and the square root of 4 is 2, not negative 2. The square root of x squared is the absolute value of x. Is that what we were hoping for? Well, when you compose a function with its inverse, you hope to get out x. But remember, we had the restriction that x is bigger than or equal to 0, in which case the absolute value is just x. Similarly, if you do take f inverse and plug it into f, once I square the square root of x minus 1, we just get x minus 1, and then the ones cancel. Okay. So here are the graphs of the two functions. Okay, the blue one is what we started with. Notice it's that parabola, but it's only the right half of it because we restricted the domain. And then there's the graph of its inverse. It's the square root function. It's just been shifted one to the right. Okay, so go ahead and work through more problems from 5.2. Try to find inverse functions and verify that they're inverse functions by taking the appropriate composition.